Hi, my name is Dan Bliss. I'm a professor at Arizona State University, and I'm going to talk about enabling RF convergence, the idea of spectrum sharing or reusing the same RF energy for multiple functions by using coarse-scale heterogeneous processors. As you can imagine, if you're developing a processor, it involves lots of people, and so I have a large and wonderful team with whom I work on this project, and you see the co-authors here. So first, we'll start talking about RF convergence, and which is the idea that we're going to use the spectrum in a more flexible, more creative way. So let's think about the future. Clearly, we're going through a transition right now where the use of the spectrum, well, from DC to daylight, is becoming more complicated. There's more stress being placed on the spectrum. And actually, there's a lot of opportunity to use the spectrum in ways that we currently don't. For historically good reasons, it was difficult to do flexible implementations of complicated computational tasks. And now we're at a point where we can transition and simply be more aggressive. And so these functionalities include sort of joint communications, radar, PNT, and other sorts of applications as well. And furthermore, you can imagine that we can start using multiple systems together in ways because we can distribute coherence across them. All these techniques, once again, basically, historically, we considered too computationally expensive, too complicated to implement, and now we're at a point of transition. So more specifically about RF convergence, it's basically the idea of co-designing systems so that we can do multiple functions. As I said before, communications, various kinds of sensing, including radar, positioning, navigation, and timing are all techniques which you can imagine doing simultaneously with the same RF energy. To do this, you need multiple sort of tools. This includes developing waveforms dynamically, which perform multiple functions, receivers that can disentangle signals, potentially diverse types of signals at the same time, which once again are implementing multiple functions. And then there's a network resource optimization, which includes how we're going to use all these different waveforms, what are the limitations of various receivers, and when lots of things are going on in the spectral environment, how do we actually control it so that it all works? But if we do this successfully, we potentially are not having RF systems interfere with each other, which is the historical way of viewing this, but in fact, increase the capabilities of the overall system. So examples are if I have a cell phone, which now has millimeter wave communications in it with 5G, I could potentially use that front end for multiple functions, not just for communications. Maybe we could do hand gesture recognition, or even potentially using that front end to actually measure physiological responses, like looking at the heart rate. In the automotive sector, you can imagine as we sort of become more reliant upon sensing between vehicles and communications between vehicles and radar between vehicles, you could imagine a common waveform that has communications, radars, and relative PNT. Since the antennas are all pointing at each other anyways, it's kind of silly for us to have separate systems doing something which could naturally be done with a single system. There are DoD potential applications. DARPA funded a program, SSpark, which considered spectrum sharing and was one of the leading programs that sort of was thinking about these sorts of topics. And certainly in our lab, we have thought about this significantly. We've implemented at the laboratory scale multiple types of RF convergence sorts of techniques. And just one example you see here, we have a communication signal and a radar return, which are overlapping. And what we can do is simultaneously decode the communications and recover the radar return signal so we can perform radar operations at the same time in the same frequency. All right, so in order to go after these sorts of applications, what do we need? Well, so we're going to try to break that sort of rigid trap that we are stuck in, which is related to you have limited engineering options because there are only certain things you can implement, and then these gets reinforced by requirements, and then that helps guide people to develop certain rigid computational capabilities, and we want to break all that. So that's what we're trying to do with our Coarse-Scale Heterogeneous Processor, which we call DASH, for domain-focused advanced software reconfigurable heterogeneous SoC. It's system on chip. This is funded by a DARPA program. And so what we'd like to have is basically the ease of programming of a scalar processor, but the efficiency of full custom, sort of like the processor that's inside your phone that does LTE or 5G modem processing. Okay, so we're gonna build this heterogeneous SoC. Right now, actually, our SoC is out at the foundry and will come back fairly soon. We would like to assure non-expert programmability. And when we do this, we can enable the next generation of RF employment. And, you know, where's my flying car after all? So let's talk about the chip and the framework which allows us to actually build this sort of system. So the first observation is that if you take a look at processor efficiency as a function of node technology, which is really a surrogate for a function of time, the giga operations per second per watt vary significantly if you compare different approaches for processor architectures. Scalar processor, the sorts of processors that we are all used to for standard sort of programming, like the ones that live in your laptop, are wonderfully easy to program, very, very flexible, but relatively speaking, inefficient. At the other extreme, full custom ASICs, where you build a chip to perform a specific function, if you do that well, then they're extremely efficient. But of course, they're built to do one function and they're not flexible at all. And in between those, we have various techniques, whether it's GPUs or FPGAs, field programmable gate arrays, that have sort of an in-between computational capability and an in-between programmability. That is, FPGAs are far more difficult to program than just a standard scalar processor, but they are more capable. So there's that sort of trade. But we would like to break that. We would like to have the capability of programmability of a scalar processor, but the efficient, which gets close to that full custom ASIC. So the second observation is that if you take a look at a particular communications task or radar processing task, there are typically a small number of mathematical operations which in fact dominate the computational cost. For a multi-antenna communication system, you might imagine that these would include the matrix multiplies that you need for covariance matrix estimates. FFTs are always expensive. QR, back substitutions for matrix inversions, and then the FECs, for the error correcting codes. Those always are relatively expensive as well. And so there's a small number of tasks which really dominate the overall computational load, and there are a large number of higher layer tasks, which in fact are relatively inexpensive, but complicated in a programming sense. So this immediately leads one to the sensibility of, well, if I can make those expensive tasks more efficient, then the overall system would become significantly more efficient. And that drives one to the idea of a heterogeneous processor. And so here we have sort of a cartoon version of what our processor looks like. We have a number of, we have an ARM cluster, which contains a number of scalar processors, which are easy to program. There's a network on chip. It's not a simple linear network, which is what the cartoon shows here. It's really sort of a matrix of connections. But that network allows us to then connect between various processors to other processors and our interfaces to the outside world. So those processors include FFTs, specific processors that are very good for doing FFTs, for FIR filters, and then we have a couple other processors too that we'll talk about in a moment. By using this together, we can get very efficient implementations of a range of applications which are admittedly domain specific, but they are still relatively efficient. So if you want to do communications or the kind of things that we want to do for RF processing, we'll be good at that. But we're not trying to say we can solve all problems. All right. So if we think about the kind of accelerators that we need, potentially there are some specialized accelerators which you can easily identify. FFTs and filters are obviously ones that we need to be very good at. But there are a general set of other sorts of things we need to be able to do, which you might not be able to define before we thought about building the chip. To address those, we have the DAP. So the DAP is the domain adaptive processor. It's basically a systolic array processor, a high performance systolic array processor. And it's almost immediately reconfigurable. So we can reconfigure it in order 100 nanoseconds. And so that allows us to, in some sense, have a flexible accelerator, which is very good at doing the sorts of linear algebra kinds of mathematical tasks that we're interested in. The second thing is, because FECs are expensive, we have a unified FEC accelerators, which is very good at doing turbo codes, LDPC codes, polar codes, the sort of expensive codes that we are now relying upon for modern communication systems. All right, so if you just had that chip, the problem is that it doesn't mean you can actually use it. So we built a software framework which allows us to actually make the processor useful. We're still maturing this framework, but we've made a lot of progress. So we start off by actually taking a look at a domain, a particular domain, the kinds of applications that you would see for, say, RF processing. And we do an ontological analysis. This allows us to determine multiple things. We have tools to take the ontological analysis that analyzes a bunch of code and sort of determines what kind of floor plan you need. And so that allows us to think about the chip, what sort of accelerators that you need, what sort of, we call them personalities you need for the DAPs. It also, we can use this for the particular code that we're developing to then go and produce the appropriate binaries that we need to implement. And in fact, because there are often multiple ways to execute a particular function, like the FFT could be done in the ARM processor, the accelerator, or in the DAP, we encode multiple ways of actually implementing any given task. And then importantly, we then train the intelligent scheduler, given the information that we have. So the intelligent scheduler can then make real-time decisions about the resource management on the chip. This is particularly important because one of the things that is often incredibly difficult to do for programming coarse-scale heterogeneous processors is the fact that resource management, which is typically done at compile time, now we have moved this to a runtime operation. And this allows us to do efficient real-time implementations. So we start with high-level C. We go through and we turn that into executable code using information that we have learned from our ontological analysis. That allows us to then run on the processor. So as I said before, the intelligent scheduler is really critical for enabling these sorts of techniques. What we have is in real time, the intelligent scheduler determines how to take the tasks. And if we're running multiple tasks simultaneously, to spread the load across the chip given the multiple accelerators that are available. And we can see here in the example, we're actually changing what sorts of applications we're running. We can see how the intelligent scheduler automatically remaps what's going on in the chip. So this reduces the reliance on expert development. And in summary, have to thank our wonderful team for enabling us to develop this amazing SoC, and very importantly, the framework, the software tools to develop this. And we are preparing to demonstrate the Dash capabilities for a variety of problems. Thank you.